All right, we're going to learn how to integrate using partial fractions. We'll do it a couple ways. We'll always use linear factors, and you'll figure out what I'm talking about in a second. We're going to have to remember a lot of things from way back when, so we need to know how to factor for sure. Common factoring is when you take out anything that is common to all terms. So here I have x squared minus 5x. Both of those terms, x squared and minus 5x, have an x in them, so I can factor it out, which means I'm just dividing both terms by x and writing down what gets left behind. X squared divided by x leaves an x, and 5x divided by x leaves the 5. We also remember quadratic factoring, where we have, an a b, and a c, and we have that thing where the AC line, you have to find things that multiply to a times c, so two factors that multiply to -6, but simultaneously can be combined by addition to make -5. So you can think maybe 3 and 2 would work, but of course, then they would have to be both the same sign. So the tricky one with this, one of them is going to be 6 times 1. And in order to make both of these true, I make the 6 negative, which means I could rewrite this equation as x minus 6 onto x plus 1. Somewhere along the same vein, we have difference of squares, and we recall if we have a square and it subtracts another square, we're allowed to factor that by taking the root of the first term, x, minus the root of the second term, 36, root is 6, and we write it again, root of the first term plus the root of the second term. And sometimes you get to do more than one type of factoring. So in this case, I could take a common factor of 2x out, leaving x squared minus 25 behind. That's a difference of squares, so to fully factor this, I would have 2x onto x minus 5 onto x plus 5. The other thing we're going to need for partial fractions is to remember how things went back in Algebra Basics. So we remember we had two separate fractions and we wanted to combine them into a single fraction over a common denominator, x minus 2 and to 2x plus 3. If I multiplied those together, that would make my common denominator. And if I wanted to create that situation, I would just take each fraction, so -1 over x minus 2, I'm going to leave some room, plus 3 over 2x plus 3, and we would multiply in what was missing to create an equivalent fraction. So we'd multiply it in both top and bottom. So if we had -1, that fraction is missing the 2x plus 3, so we'd multiply it into the bottom to make the common denominator, but we don't want to change the value. We want to keep it equivalent, so we multiply it in the top. And same with the second fraction, we need the x minus 2 multiplied in, bottom and top. Okay, what did this do for us? It's going to make a big statement over the common denominator. So we distribute the -1 on the top to make -2x minus 3. We distribute the second 3 to make 3x minus 6. And then we simplify as we can. We get x minus 9 over x minus 2 onto 2x plus 3. So that's what we were doing a few classes ago. Now, in order to make integration easier, we want to take the finished product and figure out a way to get back to two separate fractions. I've avoided revealing these shortcuts because we wanted to work on our substitution, but there is a little sneak attack you can do. If you have linear form kind of substitution possibilities. So if you can make u to be ax plus b, so that could be like 2x minus 3, it could be 3x, it could be just plain x, anything linear, so no squares or anything as part of it, then you have this shortcut here. So if you have dx over ax plus b, you can immediately integrate that to 1 over a being this value in front of the x, ln ax plus b plus c. So if we had that 4x minus 5, we'd be able to say, just by looking at it, if it had been in this form, we'd be like, oh, hey, we're going to have 1 over 4, because 4 is a, ln 4x minus 5 plus c. This also works for just kind of our u to the n integration. So if we had taken the same one, and let's say we had the integral of 4x minus 5 to the power of 2 dx. And maybe I would just expand this and do an integration another way. But if I wanted to use this shortcut, I can go straight to knowing that I'm going to have 1 over a. That's the 4. I'm going to multiply by 1 over n plus 1. That's part of our u to the n integration. So if n was 2, the power of 2, I'm going to have 1 over 3. And then I multiply it by 4x minus 5 to the power of 3 plus c, which could be written as 4x minus 5 to the power of 3 over 12 plus c. So these are handy and they'll be part of our work. So let's see how this is going to play out for us. Looking at this, maybe I could do parts and then some substitution. There's probably a shortcut that works for this. So let's make these partial fractions and see what happens for us. First things first, I'm going to write an equivalent statement by factoring the denominator, x minus 2, x plus 2 dx. Okay, now I want to break it apart. So I want to know what the pieces of this were. Well, I know to make the lowest common denominator, I could have a piece over x minus 2 and a piece that was over x plus 2. I don't know what these are for now, but I'm going to call them A and B, and they'll probably be numbers. Okay, so what I'd like to do now is make everything back over common denominators, make A and B over the same x minus 2, x plus 2, so that I can clear the fraction. So this time and this time only, we'll do it the long way. 4 over x minus 2 onto x plus 2 equals A over x minus 2, and the denominator is missing the x plus 2, plus b over x plus 2. The denominator is missing the x minus 2. And we rewrite without the bottoms, because if all of the denominators are the same, you're allowed to just drop them. So I keep the 4 from the numerator. I'm going to write the x plus 2 onto A, and we're going to write the x minus 2 onto b. So now it's a little bit of detective work. Looking at this, I want to find out what A and B could be. There's always easy choices to make. So I look to my x plus 2 and my x minus 2. Let's say I set x equal to 0. That's not that helpful, because then I'll still have two variables. But if I choose x equals negative 2, my math will become 4 equals minus 2 plus 2, and that's why I chose it, A plus negative 2, B. So I get 4 equals 0A minus 4B, which essentially gives me 4 equals negative 4B, and it tells me that B has to be equal to negative 1 in this equation. Likewise, I would probably pick x equals positive 2 next, and by the same thing get an equation that was 4 equals positive 4a plus 0b, and a must be equal to 1. So instead of integrating this thing, now I can integrate two separate fractions. I have, sorry, a was on the thing, 1 dx, or just dx, over x minus 2, so rebuilding, and I'm going to kick out that negative because b is negative 1. I'll have a minus instead of plus the integral dx, and maybe I don't need to write down that. And that's really easy because we've got that kind of lawn cheater rule, or the shortcuts for substitution. This is a linear factor in the form ax plus b, so I know that the integration right away will take me to ln x minus 2 minus ln x plus 2 plus c, which I could rewrite, and let's do it in a different color for the final answer, as ln x minus 2 over x plus 2 plus c, and done. Let's do another one start to finish. We're going to first break 6 over x squared plus 7x plus 10 into partial fractions. So we factor x plus 5 onto x plus 2 works for me. And then we know that that must be equal to a over x plus 5 plus b over x plus 2. We multiply in what's missing to clear the fractions. The a is missing x plus 2. The b is missing x plus 5, or that fraction with the b on top. There we go. Our easy values, let's set x equal to negative 2 again, because that will create 0 right here. The equation becomes 6 equals 0a plus 3b. So 6 equals 3b, which means b must be equal to 6 divided by 3, or 2. Now we're going to try x is equal to negative 5. This gives us 6 is equal to negative 3a plus 0b, and a must be equal to negative 2. We're getting pairs that are opposite all the time. It doesn't always work out that way. It just seems like it does for us. So rewriting this integral as something that's easier to do, we can take a over x plus 5, or simply kick out the negative 2, that is a, and leave it as dx over x plus 5. And then plus b, which we can kick out, plus 2, the integral dx over x plus 2. We've got that linear piece there, so we're allowed to just take the shortcut, and right away we get negative 2 ln of x plus 5 plus 2 ln x plus 2 plus c. You can combine this by all means. You could have 2 ln x plus 2 over x plus 5. All these answers are fine for me, which one you choose. Same. You could put the square back in, whatever floats your boat. Here we go again. This is the same as saying the integral of x plus 2 dx onto a factored bottom, which would be x onto x plus 1. So making partial fractions, we're saying that x plus 2 over x onto x plus 1 can be expressed as a over x plus b over x plus 1. Clearing the fractions, we're going to have x plus 2 is equal to x plus 1a plus xb. We're going to set x equal to negative 1. Oh, a little bit more math on the left side. Be careful. On the left side, we have negative 1 plus 2, which gives me 1 equals 0a minus b. So b must be equal to negative 1. And then we set x equal to 0 because that'll work for our b term. And we get 0 plus 2 is 2 equals a, and we're done. Fantastic. So we can rewrite our integral as 2 on to dx over x. So I'm just writing a over x but kicking out the 2, minus, kicking out that minus 1, dx over x plus 1. And here we go. 2 ln x minus ln x plus 1 plus c, which you could put the squared back in and have it as ln x squared over x plus 1, should you care to. Same. So we'll try again with our partial fractions. Right away, let me get my pen going here. There it is. We have x minus 1 over x onto 4x plus 1. Okay, we want to make this into a over x plus b over 4x plus 1. So we clear the fractions. X minus 1 equals 4x plus 1a plus xb. All right, let's make x equal to 0. That's the easiest one for me to look at. Our equation becomes negative 1 equals 1a. So a is just equal to negative 1. Let's make x equal to negative 1 over 4. Why did I do that? Because if I make it negative 1/4, 4 times negative 1/4 here makes negative 1 plus 1 is 0. So that zeroes out the stuff in front of the a. Okay, now a little bit of fraction math. If x is -1/4, -1/4 minus 1 is -5/4. We're going to have 0a, and we're going to have -1/4 b. Now you can do some math, or you can just recognize this is the same as saying 5 equals b. So we're going to get ready for the integration part. Then we'll do this stuff with the definite integral at the very end. We're going to have an integral. -1 is a, kick it out, dx over x, plus kick out the 5, that is b, dx over 4x plus 1. Okay, so we end up with negative ln x plus the 5 over 4. This is that 1 over a, because a here is finally not just the number 1. So the fraction comes into play. Don't forget that part of the shortcut. Ln 4x plus 1. There we go. And there's no plus c because we're going to evaluate this between x equals 1 to x equals 3. So let's just plug in some numbers, see what happens. We're going to have negative ln of 3, I can draw my absolute value, plus 5 over 4 ln of 8. And then we're going to subtract, and big brackets to protect it, negative ln of 1 plus 5 over 4 ln of 5. Okay, we can simplify this a bit. You know, this is really style points, what you want to go to. If we have negative ln of 3 plus ln of 1 plus 5 over 4 ln of 8 minus 5 over 4 ln of 5, we can create, using those log rules, ln of 1/3 plus 5 over 4 ln of 8 over 5. And you could go even further and you could put the 5 over 4 back in as a power and do a multiplication with a single term. Doesn't really matter for me. So here's the exact value of this integral. And one very last one. Okay, so we're going to take our x over 9 and put it over, or x minus 9 rather, and put it over. I'm going to factor out an x. That leaves me with 2x minus 3x plus 1. I'm probably going to have 2x minus 1 onto x minus 1 to make that work. Okay, more. Is there anything different? No, we just have to do more work. A over x plus b over 2x minus 1 plus c over x minus 1. Now, three different things. So when we clear the fractions, each one takes the other two things it's missing. So we have 2x minus 1 onto x minus 1 onto a, plus x onto x minus 1b, plus x onto 2x minus 1c. Hard to keep track of. Okay, let's start by making x equals 0. Then we get negative 9 is equal to minus 1 times minus 1a. A. So a equals negative 9. Fantastic. Let's make x equal to 1. Then we're going to have negative 8, and the a term is going to go to 0, and the b term is going to go to 0, and we just have the c term where we're going to have 1 onto 2 minus 1, 1 onto 1. Okay, c is negative 8. There we go. So far, so good. Let's make x equal to 1/2, so we clear out anything with 2x minus 1. Okay, 1/2 minus 9, oh, I just really want to do decimals, I think is minus 17 over 2 equals, and we're going to clear the a term, we're going to clear the c term, and I'm going to have to do a little more math here. 1/2 onto negative 1/2 times b. We end up with negative 17 over 2 equals 1/4 b. And then we go to, wait a second, we go to, I forgot the negative on that. But basically we're going to end up with b is equal to, Oh, yuck, 34. Okay, let's build, I'll change the color, our integration. So we're going to have negative 9, the integral of dx over x. If c, oh, we got to go to b first, plus 34. And I'm going to put this one over 2 because notice that a in this one, in the denominator, the little linear thing, has a 2 in front of it. So 34 over 2 times the integral of dx onto 2x minus 1. And then for c, we had a negative 8 over the integral, or onto the integral rather, of dx over x minus 1. Okay, so we get negative 9 ln x plus 17 ln 2x minus 1 minus 8 ln x minus 1 plus c. I don't feel like making that into anything. I'm just going to leave it as is. All right, so that's it. Partial fractions, and just to mention, we need to look at another part of linear factor. This one is what we call a non-repeating linear factor. We got to look at repeating linear factors too.